Before 1997, traveling from Kawasaki to the city of Kisarazu was a miserable task. You had to drive 100 kilometers the long way, crawling around the entire perimeter of Tokyo Bay in a grueling 2-hour detour. Every day, this parade of gridlocked trucks actively choked the economic output of the Japanese capital. The congestion wasn't a localized problem, it was a systemic drag on the region's logistics. Look at this map of the bay, and the obvious engineering solution presents itself. Just build a bridge spanning the 15 kilometers straight across the water. It's cheaper, it's faster, and it completely bypasses the congestion. But you can't. Tokyo Bay happens to be the busiest shipping lane in Asia. 4,000 vessels move through these waters every day. To clear the decks of these towering container ships and oil tankers, a bridge would require pylons of an impossible height. And this cross-section reveals the second fatal flaw. Even if you could design those massive pylons, you have nothing to put them on. Underneath Tokyo Bay, there is no solid bedrock. There's only 60 meters of soft alluvial mud, the exact kind of ground that swallows heavy foundations whole. Standard brute force construction was useless here. Since the engineers could not overpower the bay, they had to negotiate a compromise with the geometry itself. Drop a tunnel beneath the shipping lanes, build a lower bridge over the shallower water, and construct entirely new land in the middle to connect them. To transition traffic safely from an underwater tube to a surface-level bridge, they needed an artificial island right in the middle of the bay. But dropping thousands of tons of rock directly onto that soft mud guarantees your new island sinks straight to the bottom. The solution was a technology called sand compaction piles. Heavy metal tubes were driven deep into the seabed, vibrating aggressively. As they pull back up, they inject dense sand, leaving behind a rigid vertical column while squeezing trapped water out into the surrounding silt. They repeated this process thousands of times, creating a massive underground grid. By forcing all that water out, this grid of sand columns artificially increased the density of the seabed, giving it the necessary strength to hold millions of tons of dredged rock. This stabilized foundation allowed them to build Umihotaru. It looks like a 5-story concrete cruise ship parked permanently in the middle of the sea, holding a vast parking deck, shops, and ventilation facilities right over the open water. Umihotaru doesn't survive by floating, and it doesn't rest on solid rock. It stands firm because engineers physically altered the density of the seabed itself, converting unstable silt into a reliable foundation. While the island was rising, the deep dig began. They launched 8 massive tunnel-borne machines, each weighing 3,200 tons, from opposite shores, tasked with digging the 10-kilometer route under the seabed. At 60 meters below sea level, the primary threat is no longer mud, it is water pressure. The sheer weight of the ocean above pushes down against the exposed face of the tunnel with a crushing force of 6 bars. The machine pumps pressurized clay against the mud. The outward push of brown slurry balances incoming seawater pressure. Maintain this equilibrium constantly. If pressure drops, the tunnel floods instantly. Push too hard, and slurry erupts violently upward through the seabed. Surviving the deep ocean dig didn't require building thicker steel armor. It required maintaining a perfect dynamic equilibrium with the total weight of the sea, 24 hours a day. Halfway through the drive, the engineers hit the highest stakes moment of the entire project. 2 3,200-ton machines, drilling blind from opposite directions, had to align and meet deep beneath the bay, with a margin of error measured in centimeters. The mechanical problem here is terrifying. To physically join the 2 resulting tubes together, human workers have to open the sealed cutter heads. The only thing standing between them and the crushing weight of the Pacific Ocean is a few meters of saturated mud. To safely breach the steel, they drill probes into the meeting zone and pump chilled brine at -30 degrees Celsius. The surrounding water and mud rapidly solidify into an impenetrable, rigid block of dark ice. Protected entirely by this temporary frozen plug, workers cut directly through the heavy steel faces of the joined machines, opening the pathway between Kawasaki and Kisarazu without letting a single drop of seawater inside. They completed the tunnel by actively altering the state of matter of the ocean floor, using the frozen bay as a temporary shield against its own crushing weight. Once the 10-kilometer tube is hollowed out, a completely new threat takes priority. A concrete pipe trapped beneath the ocean is incredibly efficient at holding heat and smoke, making a severe vehicle fire a potential mass casualty event. This animated slice shows the hidden three-tiered architecture inside the completed tube. The central deck holds cars, exhaust beneath, and fresh air above. Escape doors connect the parallel tunnels. In a fire, drivers walk through these pressure-sealed crossovers into the safe tube. To handle the toxic smoke, this sleek structure, the Kaze no To, or wind tower, rises out of the water above the tunnel. It passively captures the continuous surface winds of Tokyo Bay, using that moving air to suck smoke out of the exhaust corridor while pushing clean oxygen in. The entire system operates on the assumption that a fire will inevitably happen. To survive it, the tunnel brilliantly co-opts the bay's natural surface weather as its primary passive life-saving mechanism. When the Aqua Line finally opened on December 18, 1997, it cost roughly $11 billion and took 9 years of labor. But the initial toll was set so high, over 5,000 yen, that almost no one used it. The project sat there like an empty ghost town. It remained an enormous financial sinkhole until 2009, when the government finally slashed the toll price. Almost overnight, traffic surged, finally making the road the high-capacity artery it was designed to be. But its ultimate structural test arrived 2 years later. In March 2011, the magnitude 9.0 Tohoku earthquake violently struck the region. Tokyo Bay shook intensely for several minutes. Cargo ships swung violently at anchor, and the intense seismic waves caused the softer edges of the coastal seabed to fully liquefy. Through all of that chaos, the Aqua Line held. The man-made islands, locked deep into the mud by those sand compaction piles, stayed firmly in place. The sweeping, segmented curves of the bridge safely flexed to absorb the violent shear forces, and the watertight tunnel seals dynamically shifted to redistribute the extreme load. Not a single segment breached. The engineers understood from the very beginning that the surface water belonged to the cargo ships, the seabed belonged to the soft mud, and the air itself was subject to the region's lethal tectonic forces. The Aqua Line succeeded because it avoided a direct confrontation with the bay's natural forces. It mapped out the immense physical constraints of the region and threaded a flexible line right through the gap left behind.